Hello and welcome to my video project presentation of my final project for IEOR262B. This project is a review of different methods that try to solve the best subset selection problem. The context for this project is the linear regression problem, in which we assume a model in which quantitative response is dependent by this linear relation on a design matrix plus some Gaussian noise. And in this linear regression setting, many times we want to select a sparse parameter vector. And in particular, we want to select the best K features to estimate our response given our inputs. Why is sparsity interesting? Mainly because it can lead to more interpretable models with less features. It can also help eliminate redundancies in our data, and it aids us in solving high dimensional problems, that is, problems that have more features than observations. And an example application of this is genomics data. This leads us to the best subset selection formulation as an optimization problem, in which we aim to minimize the least squares loss subject to a cardinality constraint on the parameter vector, which is here presented as a constraint on the L0 pseudonorm. Note that this problem is NP hard, thus very difficult to solve. This has led researchers to a series of approximate problems and approximate methods. The most popular of which is probably the lasso, which adds an L1 norm penalty to the objective function. Another variant of this is the relaxed lasso, in which a compromise between the lasso solution and a least square solution on the active set is found. And finally, a greedy feature selection procedure, which is forward stepwise selection. The background of this project in terms of literature is comprised of mainly these two works. In the first one, a discrete first order method for the k-sparse regression problem is proposed, as well as a mixed integer formulation of the best subset problem. And in the second one, a comparison of a series of methods is done with several conclusions. The goals of this project are to expand on this comparison, implementing and evaluating different approaches to the best subset selection problem according to their statistical accuracy as well as support recovery. In terms of the methods used in this project, a series of experiments will be run across different data sets using different methods for the problem at hand and evaluating different metrics. More concretely, the data sets used will be both synthetic and real. Regarding the synthetic data, different sparsity patterns, dimensionality, signal to noise ratios, and correlation factors will be used. And regarding the real data, most of it will come from applications in the genomics field. As for the methods that will be compared, the lasso, relaxed lasso, the discrete first order method before mentioned, and the best subset mixed integer formulation will be compared. Finally, the evaluation metrics used to assess the quality of each of the approaches can be classified in those metrics that measure statistical accuracy or data fidelity. For example, the relative risk, relative test error, and proportion of variance explained. And we can also talk about metrics that measure the quality of the recovery of the support or the sparsity pattern recovery, such as the number of non-zero coefficient estimates, the misdetection rate, or the false alarm rate. Results so far are limited to the low dimensional setting. And as we see here, in a setting with a relatively low correlation factor, we can examine that the relative risk of all methods decreases with the signal to noise ratio, which makes intuitive sense as there is less noise in the data, and therefore the estimations that we get are better. And in this setting, the winners per se are the lasso and relaxed lasso methods. However, if we look at another metric, such as the false alarm rate, which measures the number or the proportion of false positives per se in our coefficient vector, we see that the relaxed lasso, the best subset, and the first order method achieve a better performance than the lasso, which ends up estimating too many coefficients as non-zero. On a setting with a higher correlation factor, we see a similar performance regarding the relative risk and a more unstable result regarding the false alarm rate, which will be studied more in depth. Now I want to note that the main contributions of this project are the fact that these experiments will be run on a wider variety of real and synthetic datasets as compared to the prior work presented before. The fact that metrics measuring the support recovery have been added to the comparison of methods, such as the case of the misdetection rate and the false alarm rate. I also want to mention that the discrete first order method proposed by the aforementioned MIT researchers will be compared with other methods directly and across a wider spectrum of datasets, which was not done in the prior work. And finally, this project has brought about a Python implementation of all these methods, which can be useful for further experimentation. My work right now is focusing on experimenting on the high dimensional setting, as well as on real data, and further work will include comparing computational performance of the methods. This has been all for today, and thank you very much.